Alright, time for new DraftPhysics.com, debatephysics.com video presentation. So a little bit more on the subject of, what is the subject, frankly? Time dependency of something that comes as a rate. I mean, I shouldn't have to explain that to anybody. That the very definition of a rate is that has a lot to do with time. That time decides how much happens in a specific amount of time. It's really shouldn't have to explain it. All right, so, but I will. So I'll play some Leonard Susskind soon, but I will first paraphrase the argument as best I can. So physics does have this conflict. Okay, you got this idea of momentum. That's Newton's idea, and then you have Leibniz's idea, which didn't sell for the first 70 years or so of its existence, and somehow in the 1800s everybody got hot for it. It's when it really took off, and then that led to the creation of some notion that it's you want to know it with the force of something, you do this mgh thing instead of this mgt thing, which time is really all that momentum cares about. How much time are you doing this velocity thing? The velocity is the time component, and the faster your velocity times your mass, more energy. So the most easiest way to illustrate it is that momentum would say that twice the force, twice the speed. 3 times the force, 3 times the speed, that it's completely proportional. Mass has just as much to do with your momentum as your velocity. And so if you put something on a scale and you put 1 pound on a scale, it weighs 1 pound, okay, and you have 1 unit of energy. And then if you put a second pound on the scale, you have 2 units, okay. And you'll have the velocity. Let's just say if you use the velocity, the energy of 1 unit, it can only push 2 units at 1/2 the velocity, that kind of stuff. It's all proportional, and it frankly makes perfectly good sense. This over here basically is stating that I can have a scale, and I can put 1 pound on the scale, okay, and I get 1 unit of energy. It's 1 unit of scale reading, and then I can put a second unit mass on there, and all of a sudden I went from 1 to 3. So I got 3 for this one. I got 3 times the energy. So this can also be illustrated as, I guess, a falling argument, that somehow when something falls in the first second that it falls, the first unit of time, okay, we'll just say seconds for simplicity. This takes 1 second. The two formulas agree that this is only 1 unit of energy. This equals 1 unit of force. There's only 1 force here. But somehow when it falls this second unit of distance, another just 1 second, it only takes 1 second, but this second unit of distance somehow gives it 3 units of force. So somehow the force of gravity gives you more energy, even though there's no explanation for in what form the energy would take besides improving your velocity. So, the simple answer is this is not true. It should have never been accepted. This is not true. And the real facts are that momentum always did work. It still does work. And they just made a mess out of elemental physics by contriving some notion that the force isn't just plainly time dependent. It's just about how long you're in a force differential, and that the differential can take all kinds of shapes, but because of spherical symmetry, because there's no way to, in an imbalanced way, face a sphere. You can't interact with a sphere in some kind of way that's where you're going to get anything else but symmetry out of it. That it's always going to be the same from any angle, so no matter which way you approach it. Like with a square, you could approach a square, from this position, and it's not even. You're going to get a different amount of force here than you're going to get here or here. But a circle, it's always the same. Wherever you go, you're always got a perpendicular to the circle. You could argue that if you look at it as rays coming this way, these rays balance out. This, whatever's happening on this side balances whatever's happening on that side. And so generally speaking, you just have the same. You can't really evade always being perpendicular to the center of the sphere, and your perpendicularness to the center of the sphere means that you're going to always have the same. You just have to measure the distance from the center to you, and you'll always get the same number for the amount of force. Alright, so Susskind uses water as an example, and so in 2 dimensions, and he says, yeah, you have to think about it in 3 dimensions, but he basically talks about it in 2 dimensions. And the idea would be, in this case, he's not going to say the exact words, but it would be like you have a pane of glass, 2 panes of glass, and you're going to pump a liquid into the glass, in between the glass. So the glass, you can't change. You can't make it go thicker and anything like that. And it's non-compressible, so you can't change its density. And you're basically saying that a gravitational body is basically a drain. So it comes in at a constant pressure, and he calls this a divergence, where it comes in, and it goes out through the gravity well. And so you end up with this proportional bent geodesic idea, in the sense that the force, the pressure, gets greater and greater as you get closer and closer to the drain. So if this was a drain, you could understand that what's really happening is your size doesn't change. So let's say you're out here and you're this size. Your size doesn't change, and the closer you get, the more lines you're going to cross. So it gets into Gaussian kind of mechanics in terms of understanding how charge works and all these other things that work by the inverse square laws. Basically, it's just saying that as you get closer to a body, the constriction of the spherical body means that the force will get stronger and stronger and stronger as you get closer and closer and closer, because it's all ending up, there's going to end up being a lot of lines per square inch here, very few lines per square inch out here, and that's all it really comes down to. And so it's a very simple mechanical description of a force, and the fact that it just behaves as if it was wind or fluid, a river, any of that kind of stuff. So yeah, maybe we'll just get to the video and we'll play some of it. And it's a little slow and tedious, but you'll get the idea right away that he's using a water analogy to explain the existence of the, basically, look, he's describing it as a pushing force, in the sense that he's describing the source of the pressure, okay, as if it's pushing out, okay, and then he's going to talk about the gravity of a body as being an anti-divergence. So it's a divergence that's creating the pressure, and then it's an anti-divergence, okay, that's where the pressure goes, where it's relaxed, where it's pushed to, and such. Let's see if that works. Look at that, it did. It's preposterously too big. So we'll put it to a more reasonable size. Come on, stay there, please. Okay, thank you. Right there. And leave us begin.
This means, in a context where you can visualize it, imagine that we have a flat lake, all right, just a water thin, a shallow lake, and water is coming up from underneath. It's being pumped in from somewhere underneath. What happens if the water is being pumped in? Of course, it tends to spread out. Let's assume that the depth can't change. We put a lid over the whole thing so it can't change its depth. We pump some water in from underneath, and it spreads out. Okay.
So this is, like I said, you could equate these to Maxwell's drawings of charge, in the sense that, unlike how they draw charge. Okay, so they think the charge is basically going from one object into another object. So they'll draw positive as arrows in and negative as arrows out, and vice versa. But that's a little too simplistic for charge, but it does work for gravity. It's just pressure, and the fact is that you can understand it as pressure going from the outside to the inside. Now, obviously, there's no drain, I would argue, and the real cause of the pressure, how the pressure is dealt with, is where you start to get into what, Newton's theorem is what he calls it, Newton's idea, okay, that it all reduces to a point particle in the sense of spherical symmetry. And so it doesn't matter where the mass is. If I put all the mass, really heavy density here, or I put a bunch of lighter mass here, okay, spread out over a larger area, it's the same gravity, because all that really matters is how much mass is between this point and this point. So your gravity is going to be dictated just by how much mass there is that has to be traversed to get to you. So the idea would be is that, say something was coming through here, this is all that's going to decide is how much mass they'd have to go through, whether it's densely packed in one area, whether it's here, doesn't really matter. It's just about the fact that the mass is what's going to be causing this differential, in the sense that the force here is greater than the force coming out. So this is a drain in the sense that the force is going to be reduced, but it's not draining anywhere. It's being reduced because the Earth is in fact molten in the center, and the mass is actually absorbing the energy, and that's just the way it works. So more goes in, more force goes into the Earth than comes out of the Earth. It's not at perfect equilibrium on a gravitational level because there's stuff inside the Earth that's absorbing the energy, and we call that mass. So mass is the cause of your gravity, and it just matters how much mass there is. So essentially the point is that this made Newton's calculations a lot easier, with spherical bodies, because he could always guarantee that all he had to do was calculate the mass of the whole object and make it a point, because of the symmetry of the mass. And that nothing is going to basically be able to do the lopsided thing, okay? It's not going to happen. It's going to get sheared, and so it's always going to become symmetrical. So even though you could argue it doesn't matter where the mass is, it does matter in the sense that it really does have to be equally distributed. If all the lead was on this side of the Earth would have a gravitational differential. There'd be more gravity here than there would be over here. All right. Or you could argue it would have a very different center of gravity. The point where the center of the mass is would be a different location. I guess that's another way of arguing it. Just throwing that in.
We suck some water out from underneath, and it spreads in. It anti-spreads. It has so the spreading water has a divergence. Water coming in toward the place where it's being sucked out, it has a convergence or a negative divergence. Now,
so in another video I saw you use the term anti-divergence. So I guess he's done this more than once, because this isn't exactly what I remember him saying, but it's the same thing. He's basically using one concept, divergence, which means the spreading, and he's converting that word. Instead of just saying convergence, which is a perfectly acceptable word, he's using the negative divergence, which doesn't seem... It seems convergence is a perfectly acceptable word, so why not just use that instead of complicating it by saying there's such a thing as an anti-divergence?
we can be more precise about that. We look down at the lake from above, and we see all the water is moving, of course. It's moving. If it's being pumped in, it's moving. And there is a velocity vector. At every point, there is a velocity vector. So at every point in this lake, there's a velocity vector. And in particular, if there's water being pumped in from the center here, right? Underneath the bottom of the lake, there's some water being pumped in. the water will spread out away from that point, okay? And there'll be a divergence where the water is being pumped in.
So, and the obvious point would be is that the pressure at the point where it's being pumped out, or pumped in as he's saying, pumped out of some source, a hose or whatever, is going to be higher than it will be the further out you go. So the further out you go by the inverse square law, the spreading in both directions, the velocity reduces.
Okay? If the water is being pumped out, then exactly the opposite, the arrows point inward, and there's a negative divergence. If there's no divergence, then, for example, a simple situation with no divergence, that doesn't mean the water is not moving, but a simple example with no divergence is the water is all moving together. You know, the river is simultaneous, the lake is all simultaneously moving in the same.
So he's just talking about a relativity argument that the whole universe could be sliding sideways and wouldn't be terribly relevant to that divergence, though.
Same direction with the same velocity, it can do that without any water being pumped in. But if you found that the water was moving to the right on this side and the left on that side, you'd be pretty sure that somewhere in between water had to be pumped in, right? If you found the water was spreading out away from a line, this way here and this way here, then you'd be pretty sure that some water was being pumped in from underneath along this line here. Well, you would see it another way. You would discover that the x component of the velocity has a derivative. It's different over here than it is over here. The x component of the velocity varies along the x direction. So the fact that the x component of the velocity is varying along the x direction is an indication that there's some water being pumped in here. Likewise...
So he's not really saying anything here at all. You know, obviously, you can tell the difference by comparing two conditions, and you see a difference, and then you know something must have happened because there's a difference between one place and another place, so you know something, there was an event that made them different. You know, that's not saying much. So yeah, we'll just continue. Might be a little math here, which is not very useful either, because it's really just the concept. I mean, he's basically saying, look, the gravity is like water. It has a force potential at different locations based on how it's injecting, okay, its pressure. The fact is it pushes other objects. So the other objects are going to be motivated by whatever that force vector is. So on the surface of Earth, it's 9.8 meters per second. You go a radius out and whatever, it's 1/4 of that. And then you go another radius out and it's 1/8 of that. So it's just telling you how strong the flow is and how much of it you can collect if you're a boat. So it's clearly he's using the analogy to say it's basically that straightforward, and there's really no room in that description for the kinetic energy theory. You know, there's really no room for some idea that you know, there's any special velocity that gives you special extra energy.
If you discovered that the water was flowing up over here and down over here, you would expect that in here somewhere some water was being pumped in. So derivatives of the velocity are often an indication that there's some water being pumped in from underneath.
Changes in the velocity. Duh.
That pumping in of the water is the divergence of the velocity vector. Now,
so the obvious point is in the case of gravity, all of these, whatever this source would be of the pressure, it's even in the universe. So it matches our spherical symmetry in terms of being a drain. There's no unevenness in either the source of the pressure or the sink in which the pressure is absorbed, the matter bits.
Water, of course, is being pumped in from underneath. So there's a direction of flow, but it's coming from underneath. There's no sense of direction. Well, Okay, that's what divergence is.
The diagrams you already have on the other board behind there
Yeah.
with the arrows.
Yeah.
I gotta say, it is weird how he did these lectures. They weren't real formal lectures, and this one guy was always adding crap and, and injecting, and it's just, I don't know how instructive it was.
Is,
Yeah.
okay, if you take, say, the rightmost arrow and you draw a circle between the head and tail in between, then you can see the in and the out. The in arrow and the out arrow of a circle right in between those two. And let's say that's the bigger arrow is created by a steeper.
So it's always changing, and so, you know, you don't really got to get into that kind of minutia with these examples, you know, but it does, there's an exactly different amount of gravity from here to here. But it's a minutia, it's a tiny amount of difference. But if you just measured that difference, you have to now imply that there has to be some cause, and this isn't something that relativity is going to help you with, because you don't know where you are located, you know, in comparison to the object causing that change. All you know is there is a source in that direction somewhere that's providing a pressure where you're on some uneven side of that pressure, but there's no reason to believe that there's force popping in through every single piece of space. Okay, you really don't need to do that. You just need to say that there's a whole bunch of sources, they're all radiating light, and the total amount of photons is 25, you know.
Slope of the stream.
Oh, it's just faster.
It's going faster.
It's going faster.
Okay. And because of that, there's a divergence there. That's basically, it's sort of the difference between the in and the out.
Right, that's right. That's right. If we draw a circle around here, or we would see that more, since the water is moving faster over here than it is over here, more water is flowing out over here than is coming in over here. Where's it coming from? It must be.
So I would argue that that's technically incorrect. It's not more water. It's just that the source is coming out in rays this way, right? So you are blocking that much, and the fact that less is coming out is because you have mass. Okay, there won't be less coming out unless you do have mass, and it's really just about the fact that the outside of there, you know, this other level that you're being moved to has a different amount of gravity, but that gravity didn't affect you. So I mean, this gets a little, you know, they make this mistake of saying you're somehow going to get spaghettified in gravity because the gravity at your feet is different than the gravity in your head. But the fact is, the gravity that's affecting you, okay, actually does come from the top down. It does actually have to hit your top atoms, and it pushes the atoms below it. Just like when you go into the earth, you don't push just the surface of the earth, you push down into the earth, and you add pressure to the whole center of the earth theoretically. Theoretically, the pressure goes all the way to the center of the earth. For every rock or stone on top of the earth, that force ends up going through the earth. So even though the gravity might not penetrate you entirely, the force is penetrating you entirely. And there is no force at your foot. The level of gravity, say there was a differential of 8 here and 7 at my feet. The fact is, my feet aren't going to feel that 7 in any substantial way. So all it's going to get is, I'll draw that. There's just a much smaller differential. So this is a real technical point. I mean, it's, I don't know if it's really that valuable to go over it. But the gravity from the top, the strongest part of the gravity, isn't the gravity that's going to change for you. Because what you're really just saying is that this part of the gravity, the stuff coming in at an angle, that's the stuff that can create the difference. This line of gravity can't create the difference. So say it's 8 here, and it's 7 here, and this is where your feet are. This is where your head is. You can see that the only way your feet can get more force is your feet are going to break more lines. Okay, so if I drew more lines in here, you can see that the feet will break a few more lines. So there's going to be a little bit coming in from the sides. That'll be the 7 force. But the substance, the straight through force, is still only the 8. You can't create the 7, with this arrow. So this arrow can only be an 8 on your feet. It can only that's the only way you can get to your feet from here to here is to go through your head first. So, it's technically you're not at a 7 here for some part of the potential because it can't get to you. You can't feel a force that goes past you. You can only feel a force that goes through you.
Pump in. The fact that there's more water flowing out on one side than is coming in from the other side must indicate that there's a net inflow from somewhere else, and the somewhere else would be from the pumped in water from underneath. So,
but it would be somewhere else. It wouldn't be necessarily from right behind you. It might be a million miles away from you.
that's the idea of divergence.
Could it also be because it's thinning out? Would that be a crazy example, like the lake got shallower?
Yeah, well, okay, all right, so let's be very specific now. I kept the lake having an absolutely uniform height, and let's also suppose that the density of water is an incompressible fluid. It can't...
Right, so by those two standards, okay, it can't be a closed system. Right, so if it's uncompressible, okay, now if you're pumping new water in, there's no water in the system at all, then you can make that argument that you're just adding water to a desert. But if it already has water in it, and you're pumping more water in, clearly if it's uncompressible, you have to have a place for the water to go out. So, it is, he's pretending this is, this analogy, he thought through it very well when he, he's kind of using it casually.
Can't be squeezed, it can't be stretched. Then the velocity vector would be the right thing to think about then. Yeah, but you could have, no, you're right, you could have a velocity vector having a divergence because the water is, not because water is flowing in, but because it's thinning out. Yeah, that's also possible.
Right, so basically saying, look, we don't have any water in the system yet, and the water now is just going out, and that would make it very easy to see how the water gets weaker and weaker and weaker as it goes further and further out, because it's getting thinner and thinner and thinner.
Possible. Okay, but let's keep it simple. All right, and you can have the idea of a divergence makes sense in 3 dimensions just as well as 2 dimensions. You simply have to imagine.
Yeah, a vacuum cleaner pulling air from all dimensions. Yeah, which isn't that obvious.
That all of space is filled with water.
There we go. And water at a pressure is the key point. It's not just filled with water, it's filled with water at a pressure.
And there are some hidden pipes coming in, depositing water in different places so that it's spreading out away from points in 3-dimensional space. In 3-dimensional space, this is the expression for the divergence. If this were the velocity vector at every point, you would calculate this quantity, and that would tell you how much new water is coming in at each point of space. So that's the divergence. Now, there's a theorem which, the hint of the theorem was just given by Michael there. It's called Gauss's theorem, and it says something intuitive, very intuitively obvious. You take a surface, any surface.
So I think I might skip this just because this is, I don't know how useful it is. It's just basically telling you, look, you're going to draw a bunch of perpendiculars from any surface. And all you're saying basically is as you create more surface area, you diminish the amount of force that can be applied per square inch. So you have a certain amount of chalk, and all you're saying is our density of chalk, and it leaves a line, and our photons would probably be the better one, even the the Argo spot. The whole idea is you have a certain number of photons. The larger the area you spread them on, the less visible the photons become, and the smaller the area you spread them on, the more visible they become. So you're just saying the velocity will be dependent on how much area the velocity is spread over. So I don't think that's that critical to understand, so we'll jump ahead a little.
Perpendicular to the surface. Let's call it A perpendicular to the surface, d sigma. A perpendicular to the surface is the...
So it's just taking the integral, which just means you're just finding averages and blah, 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 blah. But it's, it all comes back to Newton's point source. So all you need to know is the center of the mass.
The amount of flow that's coming out of each one of these little boxes. Notice, incidentally, that if there's a flow along the surface, it doesn't give rise to any fluid coming out. It's only the flow perpendicular to the surface, the component of the flow perpendicular.
So they're just using the perpendicular because, again, they're talking about symmetry. That the assumption is that whatever's coming out not perpendicular is the same on either side, so it doesn't make any difference.
To the surface, which carries fluid from the inside to the outside. So we integrate the perpendicular component of the flow over the surface, that's the sigma here. That gives us the total amount of fluid coming out per unit time, for example, and that has to be equal to the amount of fluid that's being generated in the interior by the divergence.
So he's just basically saying if the thing you draw is big, okay, you're going to get a very small number per segment, and if it's small, you're going to get a high number per segment. So the velocity or the pressure at any location is going to be dependent on how much surface it's spread over. You're basically turning this any shaped object into a sphere and saying what size sphere does that make, and then once you know what size sphere it is, then you can easily calculate,
This is Gauss's theorem, the relationship between the integral of the divergence on the interior of some region and an integral over the boundary where it's measuring the flux, the amount of stuff that's coming out through the boundary. Fundamental theorem. And let's see what it says now. Any questions about Gauss's theorem here? You'll see how it works. I'll show you how it works in a minute.
Yeah, you mentioned that for water as incompressible. Does that mean if we were dealing with compressible fluid?
Well, yeah, you could have, look, sure, if you had a compressible fluid, you could discover that all the fluid out in the boundary here is all moving inwards in every direction without any new fluid being formed. In fact, what's happening is just the fluid is getting squeezed. But if the fluid can't squeeze, if you cannot compress it, then the only way that fluid could be flowing in is if it's being removed somehow from the center. If it's being removed by invisible pipes that are carrying it off.
So look, it's kind of just silly almost, but yes, what goes in, something has to come out because it's non-compressible. And the argument is that somehow gravity is that drain. But the argument is it's not draining anything. It's consuming the pressure. It's migrating the pressure from the outside and creating more of it on the inside of the object. So the inside of the object is pressurizing as the exterior dumps its pressure into the gravitational body. So every gravitational body there's more pressure at its core than there is on its outside. So it's basically consumed pressure, so it's used it, and that's why it's radiating less pressure than went in, because it now has pressure inside of it.
So that means the divergence in the case of water would be zero, would be integrated over a volume.
If there was no water coming in, it would be zero. If there was a source of the water, divergence is the same as source. Source of water is the source of new water coming in from elsewhere.
So, like I said, it really does confuse this subject, in my opinion, by talking about the divergence, I mean, the cause of the pressure, rather than talking about the drain. And, you could just say, look, we know the pressure exists, and we're just saying, where does it drain? And it's draining in the mass, and it's not really draining, it's being stored in the mass. The mass is collecting it. Let's see, is there some other way to say that that's better? It's not storing it like a battery. It's delaying it.
Right, so in the example with the two-dimensional lake, the source is water flowing in from underneath. The sink, which is the negative of a source, is the water flowing out.
There you go. So, I mean, it's a necessary element. It's just,
And in the two-dimensional example, this wouldn't be a two-dimensional surface integral. It would be the integral in here equal to a one-dimensional surface integral coming out. Okay. All right, let me show you how you use this. Let me show you how you use this and what it has to do with what we've set up till now about gravity. I hope we'll have time. Let's imagine that we have a source. It could be water, but let's take the three-dimensional case. There's a divergence of a vector field, let's say A. There's a divergence of a vector field, del dot A, and it's concentrated in some region of space that's a little sphere. In some region of space that has spherical symmetry. In other words, it doesn't mean that the divergence is uniform over here, but it means that it has the symmetry of a sphere. Everything is symmetrical with respect to rotations. Let's suppose that there's a divergence of the fluid.
So, this is where it's just sort of unintuitive and the wrong approach, because we know there's not some sort of whatever this would be, right? Some sort of antimatter that pushes stuff out. Okay, we know there's no obvious source of pressure. That the pressure essentially, by Descartesian logic, the pressure always existed. The universe always was full of these little photon-y things moving the speed of light. The pressure in space is constant. And the only thing that's changing is how much of it's trapped inside of matter. So the more consolidated the matter becomes, the more it consumes some of that pressure.
Okay. Now let's take, and it's restricted completely to be within here. It could be strong near the center and weak near the outside, or it could be weak near the center and strong near the outside, but a certain total amount of fluid or a certain total divergence, an integrated divergence, is occurring with nice spherical shape. Okay, let's see if we can...
So again, it can't have nice spherical shape if more is coming in over here and less is coming in over here. So again, it's just sort of breaking, just a poor use of the metaphor.
Use that to figure out what the field, what the A field is. There's a del dot A in here. And now let's see, can we figure out what the field is elsewhere, outside of here? So what we do is we draw a surface around there. We draw a surface around there. And now we're going to use Gauss's theorem. First of all, let's look at the left side. The left side has the integral of the divergence of the vector field. All right. The vector field, or the divergence, is completely restricted to some finite sphere in here. What is Incidentally, for the flow case, for the fluid flow case, what would be the integral of the divergence? Does anybody know? If it really was a flow of a fluid. It would be the total amount of fluid that was flowing in per unit time. It would be the flow per unit time that's coming into the system.
So that's what we're waiting for. Flow per unit time. Okay, it's all just a time-dependent force. So, yeah, it took a long time to get there, but it's that simple. All right. So it's just about how much there is, and then it's about how much you can collect whether you are by how much of the water. So a stream has a constant divergence, you could argue. The wind, it's a, you know, if it's a constant 15-mile-an-hour wind, okay. And so you just calculate how much sail you have, and you know how much wind you're collecting and how much force you're collecting. So it's completely based on, then you just calculate how much time were you in that condition where you were collecting that force. That's all there is. There isn't anything else. Yeah.
But whatever it is, this integral doesn't depend on the radius of the sphere as long as the sphere, this outer sphere here, is bigger than this region. Why? Because the integral over the divergence of A is entirely concentrated in this region here.
Right. So all you're saying is this was the opposite case, not something excreting, but something consuming. So if there's a gravity well, the argument is that it's just about how much mass is there in any diameter I could draw through this, shape. And I can have any shape, and I just say how much mass is there through any line that I can draw through the center of its mass, and that'll tell me exactly how much energy, force, has been absorbed, and how much of a differential there is in the force.
And there's zero divergence on the outside. So first of all, the left-hand side is independent of the radius of this outer sphere, as long as the radius of the outer sphere is bigger than this concentration of divergence here.
So it just doesn't matter the density of the matter. It just matters, how much there is in total.
So it's a number. Altogether it's a number. Let's call that number M. No, not M. Let's just Q. That's the left-hand side, and it doesn't depend on the radius. On the other hand, what is the right-hand side? Well, there's a flow going out, and if everything is nice and spherically symmetric, then the flow is going to go radially outward. It's going to be a pure radially outward directed flow.
Right, and this is where you can just do the cheat, of just drawing all these vectors. And you could draw 1,000,000 lines, and then you could just do your integral kind of easily by just counting how many lines at any one location you cross. So you take the same size object out here, and you take the same size object in here, and obviously the one on the inside, it has the same area, and it will cross a lot more lines the closer it gets to the object.
If the flow is spherically symmetric. Radially outward directed flow means that the flow is perpendicular to the surface of the sphere. So the perpendicular component of A is just the magnitude of A. That's it. It's just the magnitude of A, and it's the same everywhere on the sphere. Why is it the same? Because everything has spherical symmetry.
Right. So in the sphere, you're just talking about the area of the sphere. So that's when you're going to get into the 4 pi r squared, I think is the area. And so that's why there's always this 4 pi in these equations, is that's just basically saying you're talking about a sphere. And so you're just going to do the area of the sphere and just say the bigger the sphere gets, the lower the pressure gets, or the velocity gets.
Spherical symmetry, the A that appears here is constant over this whole sphere. So this integral is nothing but the magnitude of A times the area of the total sphere. Right? If I take an integral over a surface, a spherical surface like this, of something which doesn't depend on where I am on the sphere, then it's just, you can take this on the outside, the magnitude of the field, and the integral d sigma is just the total surface area of the sphere. What's the total surface area of the sphere?
4/3 pi r.
No third, just 4 pi r squared. Yeah. 4 pi r squared times the magnitude.
I don't know exactly why they do this, right? Because obviously that's a constant number, right? 4 times 3 times, 3.16, so they could give this a real number because they're not going to bother with all those extra decimal places and just say, yeah, it's a real number, but whatever.
Of the field is equal to Q. So look what we have. We have that the magnitude of the field is equal to the total integrated divergence divided by
The charge, so I think that's why I used Q, was to inject the idea that it is the density, the charge density.
4 pi. The 4 pi is just a number times r squared. Does that look familiar? It's a vector field. It's pointed radially outward. Well, it's pointed radially outward if the divergence is positive. If the divergence is positive, it's pointed radially outward.
And then obviously if it's a gravitational body, it's pointed inward. Okay, so, again, I don't know why he focused on creating anti-gravity devices more than just figuring out that there's gravity sinks. And that the sinks are either big wells, big holes, lots of water can pour down, or small holes, less water pours down. And that's really all you're saying about the velocity or the strength of the gravity is just how big is the drain. If it's a big drain, then the velocity is going to be very high. If it's a small drain, then the velocity is going to be very low. All right, it's probably enough, but he always gets tired, and so, so the endings are always kind of lame.
And its magnitude is 1 over r squared. It's exactly the gravitational field of a point particle at the center here.
It doesn't look like it. It doesn't look like you got a scale. It's the magnitude.
Yeah. That's why we have to put a direction in here.
So you really don't have to use a point particle. You could use a 1-inch particle, a 2-inch particle. You're just saying what's the total mass. That's it. And you're either making it very dense by putting it in a very small object, or you're making it very, like the sun is hydrogen. It's really big, but it doesn't create all that much gravity. So it's 1,000,000 times bigger than the Earth, but it only produces 80 times the gravity on its surface. So there's a huge divergence, okay, between the number 80 and 1,000,000. And it's all based on the fact that basically the elements that make up the Earth are that difference in weight to hydrogen. So they weigh that, whatever, 178,000 times more, okay, than the hydrogen atoms that the sun is made out of.
You know what this r hat, this r over r is? It's a unit vector pointing in the radius.
It doesn't mean anything, right? So that's just there to say, we're just saying it is a vector, so it has got a direction and a magnitude, and that's all it's saying. So it doesn't mean anything. It's a 1 with an arrow over the top of it. So it's really, I don't know why they resort to such shenanigans.
Direction. It's a vector of unit length pointing in the radial direction. Right. So it's quite clear from the picture that the A field is pointing radially outward. That's what this says over here. Right. In any case, the magnitude of the field, it points radially outward. It has magnitude Q, and it falls off like 1 over r squared, exactly like the Newtonian field of a point mass.
Right. So just okay. So it's probably enough. There's just, I don't think he's going to do anything here. Well, We'll finish it since we're here.
So a point mass can be thought of as a concentrated divergence of the gravitational field right at the center. A point mass, a literal.
So this doesn't make any sense, right? So he said this is just him misspeaking. So he's saying a point mass can think of it be an anti-divergence. Okay, so his own rhetoric is screwing him up. He should be just saying, obviously it's a convergence in the case of a point mass. A point mass is not creating external pressure, it's consuming external pressure. It's a drain, it isn't a faucet.
Point mass can be thought of as a concentrated divergence of the gravitational field.
Going in.
Concentrated in some very, very small little volume. Think of it, if you like, you can think of the gravitational field as the flow field or the velocity field of a fluid that's spreading out. Oh, incidentally, of course, I've got the sign wrong here. The real gravitational acceleration points inward. Which is an indication
of a convergence.
That this divergence is negative.
Yes, it's a negative divergence.
The divergence is more like a convergence.
Yeah, it's exactly like a convergence. It's not more like, it's exactly like. But okay. It's just language. I really don't see any use in bending words this way.
Sucking fluid in. So the Newtonian gravitational field is isomorphic, is mathematically
I should be back.
equivalent, or mathematically similar, to a flow field, to a flow of water or whatever other fluid, where it's all being sucked out from a single point. And as you can see,
and it's all time dependent, how much of it crosses any diameter, any surface, any line you want to draw. There's a certain volume that will cross that volume in a certain amount of time, and that's the force. And there's a certain amount of that force you can collect if you have a certain mass.
The velocity field itself, or in this case the field, the gravitational field, but the velocity field would go like 1 over r squared. That's a useful analogy. That is not to say that space is a flow or anything. It's a mathematical analogy.
Yeah, it's not to say it is rain, but yeah, it behaves just like.
Analogy that's useful to understand the 1 over r squared force law.
And that one, I just don't understand why we need anything to understand it when photons are doing it all the time. A light bulb is doing it. So what's so hard to understand? And again, you can illustrate it just, yourself. You can just do it and see it happen, Half the distance, 4 times the volume of hand. Okay.
That it is mathematically similar to a field of velocity flow from a flow that's being generated right at the center at a point. Okay, that's a useful observation, but notice something else. Supposing now, instead of having the flow concentrated at the center here, supposing the flow was concentrated over a sphere which was bigger, but the same total amount of flow.
Right, so that's the hard part, right? You can't really make the drain bigger, so you can't really make a density argument, but he's basically saying, let's take this, let's have a little tiny lead ball, and let's instead have a lithium ball, that's much bigger. Same mass, just bigger. Same gravity, same force on that exterior line. It doesn't matter. It's just how much mass is there. If you draw a diameter across that center, how much mass are you drawing that line through?
It would not change the answer. As long as the total amount of flow is fixed, the way that it flows out through here is also fixed. This is Newton's theorem. Newton's theorem in the gravitational context says that the gravitational field of an object, right, outside the object, is independent of whether the object is a point mass at the center or what.
Whether all the mass was a single location in space, or whether all the mass was a baseball, or whether all the mass was a a basketball, all the mass was, just get bigger and bigger. As long as it's spherical, it just can't make any difference.
Whether it's a spread out mass, or whether it's a spread out mass.
It's just the amount of mass that's creating the mass between you and over there. However much mass is between you and over there is going to decide how much force, you're going to be pulled by gravitationally.
This big. As long as you're outside the object, and as long as the object is spherically symmetric, in other words, as long as the object is shaped like a sphere, and you're outside of it, outside of where the mass distribution is, then the gravitational field of it doesn't depend on whether it's a point, it's a spread out object, whether it's denser at the center and less dense at the outside, less dense in the inside, more dense in the outside. All it depends on is the total amount of mass. The total amount of mass is like the total amount of flow through coming into the.
So in a sense, let's see if I can. I can't probably use the same analogy. I'm just trying to figure out how if the sun was made out of the same material the Earth was made out of, how much smaller it would be. Okay, that kind of argument. How much bigger is it really than the Earth in terms of its total mass? So you'd have to figure out its pressure at the same radius that the Earth is, and so that I don't know. I mean, obviously the surface of the sun is a gigantic surface, so 80 times the gravity isn't much, but over that insanely large surface, it's a lot of gravity being produced to anybody who's flying by the sun.
That theorem is very fundamental and important to thinking about gravity. For example, supposing we are interested in the motion of an object near the surface of the Earth, but not so near that we can make the flat space approximation. Let's say.
So this is the important part, where it's just basically saying, look, you can average things. The force is coming. Well, this again is just about spherical symmetry again, but I'm just saying this can't hurt.
At a distance 2 or 3 or 1.5 times the radius of the Earth. Well, that object is attracted by this point, it's attracted by this point, it's attracted by that point.
So it's not really attracted by points, it's attracted by lines. So there's lines of force that are going through all kinds of sections that still get to you. So you could draw a bunch of these lines through cuts through the Earth, and every one of those lines is going to be producing a gravitational effect. But the fact is, because of the spherical symmetry, I can just draw the one line through the center and just approximate whatever's on one side or the other side. I don't have to bother because they're going to equal each other.
It's close to this point, it's far from this point. It sounds like a hellish problem to figure out what the gravitational effect on this point is. But no. This tells you the gravitational field is exactly the same as if the same total mass was concentrated right at the center. Okay?
So, but this is a conditional fact. See, the way he's drawing it, like, okay, let's say we had a big pile of lead here and a big pile of lead here inside of a body, an Earth or something. Then it wouldn't have even gravity. It wouldn't create it evenly. But the fact is that nothing can get as big as the Earth and be spherical and have that unevenness. It'll be ripped to pieces. So nothing can have that unevenness. So you can just make the assumption that all the spherical bodies are also, their density will end up being proportional in the sense that they will have light stuff on the outside and heavy stuff on the inside, and they will have to perform that will have to happen. And that's the only way they can survive. They can't survive if they don't redistribute their mass, because then they're lopsided and they're going to be sheared into pieces. So,
That's Newton's theorem. And it's a marvelous theorem. It's a great piece of luck for him because without it, he couldn't have.
Well, it's not luck, and second, yeah, it just makes doing all the calculations a lot easier if you have spheres because, you know, you got, like I said, all you have to know is the mass of the body.
Solved his equations.
You don't have to worry about angles. You're not talking about whether the square surface is going this way or the square surface is going this way.
He knew. He had an argument. It may have been essentially this argument. I'm not sure exactly what argument he made. But he knew that with the 1 over r squared force law, and only the 1 over r squared force law, wouldn't have been true if it was 1 over r cubed, 1 over r to the 4th, 1 over r to the 7th. With the 1 over r squared force law, a spherical distribution of mass behaves exactly as if...
I don't know how it changes if it's 1 over r cubed, frankly. I don't see how that would change anything except it just changes your numbers. You know, a cube law just means that it gets weaker even quicker. But whatever.
all the mass was concentrated right at the center, as long as you're outside the mass. Okay? So that's what made it possible for Newton to easily solve his own equations, that every object, as long as it's spherical in shape, behaves as if it were a point mass.
So if you're down in a mine shaft that doesn't hold?
That's right. If you're down in the mine shaft, it doesn't hold. But that doesn't mean you can't figure out what's going
Well,
on.
obviously it does hold. That's right. See, obviously the simplicity is still there because, again, all you're trying to do now is calculate how much mass is on one side of you versus how much mass is on the other side of you. And it's the same straight line vector kind of crap. And so it's not that you can still calculate based on considering yourself a point particle.
You can figure out what's going on. I don't think we'll do it tonight. It's a little too late. But yes, we can work out what would happen in a mine shaft. But that's right. It doesn't hold in a mine shaft.
So now he's going to talk about the hollow sphere. And I just thought, again, he did that kind of not really acknowledging, why it happens that there's no gravity inside the hollow sphere.
For example, supposing you dig a mine shaft right down through the center of the Earth, okay? And now you get very close to the center of the Earth. How much force do you expect to be pulling you toward the center? Not much. Certainly much less than if you were...
Right, but this is this is where, again, thought experiments go wrong because the fact is the amount of pressure there, though, is insane. So to even make your tunnel would require you to have incredible, the amount of pressure you would have to apply to keep your vessel. It's like that submarine that blew up just going down in the ocean a little bit. It got crushed by the pressure. So the pressure is insanely intense at the center of the Earth. So there's no point in talking about how, there's no force. Well, yeah, there's a ton of force. The force of gravity is affecting everything else around you. So you couldn't escape that pressure. So it's kind of very unrealistic because the pressure at the center of the Earth is insane.
If all the mass were concentrated right at the center, you got... it's not even obvious which way the force is, but it is toward the center, but it's very small. You displace away from the center of the Earth a little bit, there's a tiny...
So the gravity affecting you personally is very small. But the gravity that's affecting, what it's doing to each piece of matter, obviously all the matter above you, the force isn't small. And above you means in both directions. So both directions are effectively above you, heading towards the surface. So you're going to be crushed from both directions.
Tiny little force. Much, much less than as if all the mass was squashed toward the center. So, right, it doesn't work for that case. Another interesting case is supposing you have a shell of material. Okay? To have a shell of material, think about a shell of source. fluid flowing in. Fluid is flowing in from the outside onto this blackboard, and all the little pipes are arranged on a circle like this. What does the fluid flow look like?
I see that just doesn't, why doesn't he just say, look, I have a ring of matter, okay, and we're just going to think of it being a sphere, but a ring will work too.
In different places? Well, the answer is on the outside, it looks exactly the same as if everything were concentrated on a point. But what about in the interior? What would you guess? Nothing. Nothing. Everything is just flowing out away from here. And there's no flow in here at all. How could there be? Which direction would it be in?
So this is the part that's just wrong. There is flow. It's just that it's perfectly even in both directions no matter where you are. So the force of the gravity. So the closer you get to one surface, you have very strong attraction to a very small amount of surface. And on the other side, you have weak attraction to a very large surface. So there's a whole bunch of photons that can hit you from this direction and very few sources from this direction. So the closer you get to the surface, no matter what surface I go next to, I'm exposed to much fewer sources facing me, so if the curve is right here in front of me, there's very few sources I can see. But behind me, there's a ton of sources hitting me from the other side. So it ends up being the same amount of light. So no matter where I move, there's always the same amount of light, because if I move towards the surface, I'm getting light from fewer sources in the front, and I'm getting more light from more sources in the back. So the more I move towards one surface, the fewer sources in the front and the more sources behind. I think that's a much better way of describing this.
And, so there's no flow in here.
Wouldn't you have the distance argument? Like, if you're closer to the surface of the inner shell,
Yeah.
wouldn't there be more force towards that?
No, you see, you use Gauss's theorem. Let's do Gauss's theorem. Gauss's theorem says, okay, let's take a shell.
So I mean, really, theoretically, he's just wrong to say this is Gauss's theorem kind of appropriate, because the fact is, when you are closer, there will be more gravitational effect from the matter right in front of you. So here's a whole bunch of matter right in front of me. There's even more matter behind me, but it's further away. And the fact is those two forces will be exactly the same. As I get closer this way, I end up getting further away from that, but there's more sources. It's a real circumstance. It's not like there is no force.
The integrated field coming out of that shell is equal to...
There are two different sources, right? I mean, the two sides are two different gravitational sources. So you have to say, if I'm standing right in the middle, I'm going to know it's like having a moon on that side of me and a moon on that side of me. I have two different gravitational sources. And all you're saying is no matter where I move between those two sources inside of a sphere, I can't change how much both total light I'm getting hit by. I'm always going to be hit by exactly the same amount of light.
The integrated divergence in here. But there is no divergence in here. So the net integrated field coming out is zero. No field on the interior of the shell, field on the exterior.
So there's plenty of gravity in between two moons. It's just that in between two moons, the plenty of gravity doesn't mean anything. Like I said, if I could make the moons gigantic and I could be in between them, like there were infinite planes, okay? So if I had an infinite plane of mass and an infinite plane of mass, how else can I describe it? Well, I mean, you have to just understand it, that, from the analogy, if I just made 10 LEDs there, you could understand that if I get really close to one LED, that's all I can see on this side. And the other 9 can hit me from behind now.
The shell. So the consequence is that if you made a spherical shell of material like that, the interior would be absolutely identical to what it would be if there was no gravitating material there at all.
It would be exactly identical to being in between two equal sources. So no matter where you move, you basically are in between two equal sources of gravitational potential. A very big source far away and a very small source close. Doesn't matter how you arrange it. You can't change that. So as you move in the circle, you're basically making one source very big and one source very small. You're getting close to a small one and further from a big one. And it's always going to equal out to the same force net, which will be zero. So there's net action, but there's not zero force.
On the other hand, on the outside, you would have a field which would be absolutely identical to what happens at the center. Now, there is an analog of this in the general theory of relativity. We'll get to it. Basically, what it says is the field of anything, as long as it's spherically symmetric on the outside, looks identical to the field of a black hole.
Yeah.
I think we're finished for tonight.
I think we'll miss that.
Go over divergence and all those Gauss's theorem. Gauss's theorem is central.
All right. So a little boring, but just for context, using fluid type analogies, using anything that's a moving substance, those analogies do fit what gravity does. They're perfectly appropriate analogies to the function. All right. So, like I said, in other examples, he uses how that flow affects something sitting in the flow, and that basically it just collects it based on the mass. So the mass tells you how much of the velocity vector you will collect. All right. So till the next time and such, we'll call that a video, I think, and move along.